Mrs. Pesic here.
And Miss Bella here.
And today we are looking at section 4.2, inverses of relations and functions. So we're going to start off. Our learning objectives are to graph and recognize inverses of relations and functions, and to find inverses of functions.
You'll notice that in this section we'll have two different vocab words that we'll be learning about or highlighting, which are inverse relation and inverse functions. So to get us started, you may have seen the word inverse used before in various ways, and we've talked about well, let's pretend that she didn't just draw right over it. Okay, there we go. So we've talked about an additive inverse, and we said additive inverse, that's what would you add to 3 to take it to 0, or its opposite, which would be negative 3.
Okay, and the multiplicative inverse of 5 is 1/5, which gives me what I need to multiply 5 by to get 1. I would need to multiply 5 by 1/5. So those two are inverses.
Now, we also talked about matrices and the inverses of those. So if we had the matrix A, we talked about the notation for the inverse matrix A, which we had our calculator find for us. Remember, if we multiplied A times its inverse, we found out that A times its inverse was actually equal to the identity matrix. So matrix A times the inverse of matrix A would have given us the identity matrix, which remember had those 1s and those 0s with the 1s on the diagonals.
Also apply and find inverses and apply them to relations and functions. So to graph the inverse relation, you can reflect each point of your relation across the line y equals x. That's just like switching the x and y values in each of the ordered pairs of the relation.
Now, just a little remember here that the word relation, that means a set of any ordered pairs, and a function is more specifically a relation in which each x value has at most one y value paired with it. So that would mean that you cannot repeat the x's in your ordered pairs.
So a function would have to pass a vertical line test.
Correct.
But a relation, there's no such one. It can have many points along the vertical line.
Okay, so we're going to jump right into our first example here, graphing inverse relations. So we kind of have some steps here. We're going to graph the relation and connect the points. Then we'll graph its inverse, and we're going to actually find the domain and range of each relation. So we're going to use our graph here, and we're going to start off by graphing the 4 ordered pairs that are in our relation. So we'll graph the point 0, 2, so 0 on the x, 2 on the y, 1, 5, 5, 6, and 8, 9, excuse me. Okay, so we're going to graph those. That's just kind of our first step here, and we're going to connect those together.
I hope you're doing this yourself on some graph paper for your notes. Okay, now we are going to switch the x and y's. So if we switch the x, y patterns here, instead of 0, 2, we'll have 2, 0. Instead of 1, 5, 5, 1, we'll have 6, 5, and 9, 8.
Okay, so we're going to then go ahead, let's graph the inverse on the same grid, and we're going to use a different color here so we can identify what's the inverse, what's the original. So we have the point 2, 0, 5, 1, 6, 5, and 9, 8. And then go ahead and connect those. Okay, now if we, back to the definition of what an inverse relation or function is going to be, it actually reflects over the line y equals x. So we're going to draw in there that dotted line. That's the reflection, the symmetry. If you were to fold your graph on that dotted line, the blue and the red, those two functions would, or relations I should say, would match up with each other. Alright, so to finish this one up, we just want to say what's the domain and the range of each of these relations. So let's start off with the original one in blue.
Say goes from 0 all the way to 8?
Yes.
Alright, so the domain is from 0 to 8, and you know our notation with interval notation would look like this.
And then, so remember, domain were the x's, and our range is going to be the y, so the lowest y to the highest y, which looks like in this case that it's going to be from 2 to 9.
Alright, because that's the height, goes from 2 all the way up to a height of 9. Okay, and then what about the inverse?
Okay, so for inverse for our domain, again, our x's, left to right, the lowest or smallest x would be 2.
Okay, because we're looking at these numbers here as our domain, so from 2 to 9.
2 to 9.
And we can also look here, our domain is equal to 2 over here to 9. That's how wide our function is.
And then what about our range, our y values, lowest y to highest y? Looks like our lowest y is at 0.
Okay, all right.
Lowest y is at 0, and our highest y goes all the way up to 8.
Okay, wait a second. These look kind of familiar because it looks like the domain from our original is the same as the range from our inverse.
And that always is going to be true. Remember, the definition of an inverse is that x and y switch. So the x's in the original now become the y's in the inverse.
Okay, so that means the range of the original is going to be the same as the domain.
Again, because the y's there became the x's in this one.
Okay.
All right. So you guys have your first must do. We're going to do the same thing. So we gave you a new relation. So graph it, connect the points, find the inverse, and then again find the domain and range of each relation.
Okay, so you're going to graph this setup and then switch all the ordered pairs to get the inverse, just what we did in the last example. So go ahead and pause and do that, and then when you're ready, move on to the next.
Alright, now when we talk about a relation, when it's also a function, so if it passes that vertical line test, we can write the inverse of the function f of x as f inverse of x. Notice there's a -1 in the exponent part, but we're going to notice that this does not indicate a reciprocal. So this is not like a -1 power.
Right, so f inverse of x is not the same as 1 over f of x. That's what we know.
Right, and so that just is a symbol we use for inverse function. So functions that undo each other's operations will be called inverse functions. So our example here in these boxes, we talk about having an input of 3. So if we have something that's an input of 3, we're looking over here, and it goes into a function that adds 6 to it, well then my output would become 9. Its inverse would then put the 9 into a function and do the inverse operation, so subtract 6, and my output would become 3.
So the inverse of adding 6 to a number would be subtracting 6 from a number?
Sounds good.
Okay. So to find the inverse function, use the inverse operation. So in this example that we just looked at, 6 is added to x in the original function, so 6 is subtracted from x in the inverse function.
Okay. Right, so we're going to do a couple examples just to see that pattern. So example 2, again, we're going to write these inverses just by using the inverse operations for our functions.
So it's kind of informal defining.
Yeah,
so
just
we're
like
not having to do any serious calculations. We're just kind of taking a look at the function and saying, what's the inverse of this function?
right, kind of finding a pattern almost.
Right.
So in the first one, if we know the original function is f of x equals x minus a half, what would kind of be the inverse of subtracting a half?
The inverse of subtracting 1/2 would be adding 1/2.
So our inverse, f inverse of x, is x plus 1/2.
Okay.
What about our second one here? Again, using inverse operations. F of x equals x divided by 3.
Okay, the inverse operation of dividing is multiplying.
I think that looks good.
So we'll write f inverse of x equaling 3 times x.
Okay, and again, they should just undo what the other one has already done. Now let's get a little more formal on how we're going to do this. Another way to find inverse functions is we're going to take the original function with x and y, and we're going to switch the x and y values around and then solve for y again in the new equation.
So in other words, when they get more complicated like this one, it's going to be pretty hard to just fix that just by looking at it like those last two examples.
Exactly. So we actually want an algebraic way to go about finding this.
Right, so we're going to start by rewriting f of x as y. So we get y equals -1/2 x minus 5.
Okay, so that's still the original. So to find an inverse, the first thing we'll do is we'll switch x and y.
Okay, so we'll write x equals -1/2 times y minus 5.
Okay, and now we're going to go in and try to solve for that new y value.
Okay, so this is something we really reviewed early on.
We did.
About solving an equation for a variable in the equation. So if we want to get y by itself, we need to get this term by itself first. We need to get rid of this 5. So let's add 5 to both sides. So we get x
now I want to get the y alone, so if it's multiplied by a negative 1/2, can I multiply by its reciprocal?
Sure. So we multiply by a -2/1.
Okay.
And I better put a parentheses around this whole thing because we have to multiply the whole side by -2/1.
Alright, now should we distribute over here on the left?
Sure. So you have -2/1 times x, that's -2x, minus 10.
Is equal to,
And over here, the 2's are dividing out,
okay,
and the negative times a negative is a positive, so we just have equals y.
equals positive y. Now, since we have y solved for, we know it's a function, how can we make sure we know that this is actually the function's inverse that we found?
Okay, so can we write it as inverse of x equaling -2x minus 10?
I think that makes it a little more clear.
Can we actually check that these really are inverses by looking at the graph?
Sure. Alright, why don't we graph the original one? What do we want to graph it in? Blue? Okay. Alright, so if we graph that first one in blue, that looks like a linear function in mx plus b form.
Okay, so the y-intercept is -5.
Uh,
So I start right there on the y-axis.
It looks like my slope is negative 1/2, so down 1, 2 to the right.
Okay. To the right or up 1 to the left.
Alright, so let's draw that in.
Okay, that's the original function.
Alright, just scroll down just for a second. Right there's my inverse, -2x minus 10. Again, that one's also in slope-intercept form. We'll do this one in red.
So I've got a y-intercept of -10.
Now, if I do the same thing, if I went, isn't that really -2/1 to help me out?
Down 2 to the right 1.
Yeah, that kind of goes off my graph.
How about up 2 to the left 1?
Alright, I think that would help out here.
Okay.
Alright, so let's draw that one in. Okay, and now to make this a little more clear, if I really can tell if they're reflections, why don't we draw on that line y equals x, which is that diagonal kind of going from the bottom left to the top right.
Well, this is the equation.
Y equals x, which makes sense because x and y switch, so that's the point where they would match up.
Hey, they are reflections over that line.
Again, so if I folded along that dotted line, the red and the blue would match up with each other. It'd be like mirror images of one another.
Like this piece here gets reflected over the line and ends up down here. And this piece here gets reflected over the line and ends up over here.
I think that looks good. Okay, so in your notes you have another must-do. We'd like you to do the same thing. So you're going to take the function f of x equals 2/3 x plus 2 and do the same process. So you're going to find its inverse.
So start by writing y equals 2/3 x plus 2.
Right, then you'll switch the x and y and solve for y. Once you have your inverse, why don't you graph the original, graph its inverse, and make sure there are reflections over the line y equals x. Oh, and actually that ends our notes for today.
That ends our notes, so that's it for this time. Make sure you take good notes, write down a question for your Algebra 2 teacher, and we'll see you next time.